I remember a couple of semesters ago, every class they did the countdown. It was quite amusing. They just started spontaneously. All right, so at the start of each lecture, as in each 2 hours, I didn't do it the first hour here, I'll ping up a slide like this, which will say what's happening, anything interesting. If you think you're enrolled, but you can't log into WebCMS, send a mail to the class account and we'll see. If you're enrolled today, you won't be able to access WebCMS until tomorrow because all of the enrolment stuff gets updated overnight. Right, so in this lecture I'm going to talk about this stuff. Hopefully I'll get a fair way into it. And in the next lecture we're going to start talking about how you represent data at a very low level. Right, so one thing about the WebCMS forum, a lot of people don't like it, and that probably includes me a bit, because it's not a forum. There may be a link labelled forums, but it's not like Ed and it's not like Piazza. It's different, and I blame Richard Buckland for it because I copied what he did in Open Learning into WebCMS. So basically it's all about all of the comments that you make or all of the threads of discussion that you have are in the context of a particular page. So you can kind of think of each page as being like giving you a topic, and each new comment that gets posted there is kind of like starting a thread in a conventional message board. So the idea is that if you're working away on the lab and you discover something weird about the lab and you want to make a comment or you want to ask a question about it, you do that on the page where you're looking at the lab. That's the idea. One little trick is you actually need to subscribe to stuff. Otherwise you won't get informed about new posts on that thread. So if I go to WebCMS and I'll go to the Q&A page, all of the comment sections will have a little icon like this. If you click on that and it goes dark, it means you're subscribed. So any future comments that get posted to that page, you'll get alerted via email. If you do that and it's now gone pale, it means you're no longer subscribed to that page, so you won't be informed about stuff that happens there. So, you know, for example, while you're working on the assignment, you want to know what kind of questions are being asked about the assignment, subscribe to the assignment page. Yeah, don't boast on the home page, but people are doing that nicely. Right, if you want to change your tutor lab, yeah, we can do that. We can do it relatively easily as long as there's room in the lab that you want to change into. That's fine, and as long as the tutor is happy to take you. It's polite if you do want to change to tell the tutor that you're abandoning them. Okay, so I'm not coming to your tutor anymore. I'm going to XYZ's tutor because I reckon. Well, don't say this last bit because I think he's a much better tutor or she's a much better tutor. Don't say that. Just say I decided to change. It's more convenient. To do the other thing. There's no real point changing classes in my UNSW. The one reason you might want to do that, the one danger of trying to do that, is I think you have to drop the course and then enrol in the lecture and a different tute, and in the meantime someone else might come along and grab the spot. The only reason to do that is it's going to update your timetable, the timetable that you get out of my UNSW. But we found it's a lot more convenient to just change things in the WebCMS pages, so we keep the tute lab roles up to date that way. Anyway, you can do that. Alright, so as I said, I want to talk about at the start of each lecture, we're in the middle because I had other stuff to do at the start, talk about famous computer scientists who've invented stuff that's important in this course. Now, since all these slides have been up on the web, I'm sure someone's had a look at them. Who are these two? What? Thank you. Who said Dennis Ritchie? Yeah, that's one of them. What about the other one? Thank you. Cool. Well done. Ken Thompson, Dennis Ritchie, what did they do? If you're sitting there looking at the command line and hating it, then it's their fault because they invented Unix. Along the way, they also invented the C programming language, regular expressions, which you may or may not have had much to do with. If you do COMP1521, you'll have a lot to do with regular expressions and the whole idea of pipes. Now, back in before 1970, computer systems were large, monolithic, and bug-ridden, and very difficult to port. So they were typically developed in assembly language, and once you start writing code in assembler, you'll see why writing any large system in assembler is going to be extremely bug-prone. Operating systems were large, buggy, non-portable. They decided, I reckon we can do a better job if we write the operating system largely in a higher level language. But there wasn't a suitable higher level language at the time, so they invented C. And they wrote most of the operating system in C, and there are a few, the device driver level had to be written in assembler. Why is that a good idea? Well, because you're writing in a high level language which isn't machine dependent, you can take the operating system code, stick it on another machine, and the only parts you have to rewrite are the low-level device drivers. So that makes the operating system portable, which was a big advance on the operating systems that existed at that time. So very influential, and of course, Unix took off, blah, blah, blah. Universities started using it, then lots of other people started using it. Then it got a bit commercialised, and then Linus came along in the early 90s, once Unix had been a little bit too commercial, and decided he wanted to write his own version of Unix to put on his laptop, so he wrote Linux, and then that took off because he open sourced it, and that's what we're using today. Right. So anyway, very, very important work that those two did to come up with that idea of a portable operating system. Alright, let me see, where were we? Alright, yes. Okay, so here's a little program. It does a hash include, it does a hash define, and I have a bad feeling that my version of this code might have a lot more in it than just that. And then it makes use of the hash define, and it uses printf, so it wouldn't actually work unless we also hash included standard.io.h. So if you're really keen, where am I? By the way, all these exercises that I do in the lecture will be attached to the website after I've done them. Alright, so here's x.c, so I think I might just comment out hash include standard.io, and I'll show you why I commented out in a moment. Hash include x.h, I'm not exactly sure what's in x.h, we can have a look at it, and that's the program. Right, so what's in x.h? So it's got another hash define, and it's got a type def in it, okay? If I want to see the first stage of the C compilation, I can go GCC minus E. Why is it minus E? I have no idea. But if you did man GCC, one of the things that would show up is -C, just runs the preprocessor. So let's do that. Right, so one thing that's done, the hash include of x.h gets that statement inserted into my program. It's inserting a whole lot of other stuff here, but they're really just comments. Okay. Then here's the main program, and here we can see that x was assigned num has now been replaced by x is assigned 10, which was the hash defined for num. The other hash defined, that was 100, has just vanished. We did a hash define, but we never used the symbol that we'd hash define, so it just goes away. Okay? So that's the new version of the program, and then if I was to go GCC minus S, oh, well, let's, I think. Now I could try to call it x prime, but of course the shell treats quotes as special, and that would be slightly annoying, so let's just call it x prime dot c GCC minus S. So the next stage in the pipeline does that. That's fine because I hadn't mentioned printf anywhere. But if we have a look at what's been produced, we now have a bunch of assembly code representing the program, representing the C code that was produced from the preprocessor step. This is not MIPS assembler. I think it's X8080 whatever, which is actually the machine code, I think, that's used in that book that I mentioned, the black book. Can we see anything interesting? Yes, we can see that there's a main, which has got an underscore stuck in the front of the name. You can also see a call to printf, which once again has an underscore stuck in front of it. So, and then we've got the string hello inserted into the code as an ASCII string null terminated, which is what that .ASCII-Z means. And you can see that that's in a different section of the code. So we were talking before about how the memory is laid out. All of this stuff up here is going to end up in the code section of memory. This is going to end up in the global data section of memory because it's a constant, and constants in global data go into that section. Alright, and then of course if we go GCC minus X, what's going to happen? Wow, I can't believe it. Wait a minute. Why did that work? Oh, alright, GCC must have included some of the libraries all by itself. It was supposed to complain about printf not being defined. But there you go. So that was what that program was supposed to do. That's all it did. So you can see that there's these steps. Start from the initial C program, which has a whole lot of hash includes and hash defined. The preprocessor gets rid of them, gives us a new version of the C program, which is then parsed and turned into assembly code, and then turned into machine code and linked in with all the libraries. Let's have a look. If I take away the comments in front of that hash include, so now standard IO is going to be hash included. And it's a Mac, so it's got a whole lot of long path names. This is what ends up being inserted into my tiny little C program. Blah, 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 blah. So by hash including standard io.h, all this other stuff gets put in here. I think the stuff above came in because standard io.h hash included some other stuff. But finally what we get down to is the really interesting stuff that we're getting from standard io.h, which is the function signatures for the various functions. So fprintf, fopen, fputs, fread, and so on. GetC reads from a file descriptor, returns an int value. And still going, we haven't actually reached our little main program yet. La, 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 la. And finally we reach down here. So all of that other stuff gets inserted into our code. A lot of it we don't need, but some of it is important. So now we know what the definition of printf is because of all that other stuff that got included above. Right, so when you know, there's a lot going on behind what happens when you just type GCC and you end up with a.out. All right. That wasn't what I wanted. This is what I wanted. Right, so now I wanted to take a look at some of the other aspects of C, apart from that pre-processor stuff that you might not know about. Right, so what I assume that you can do, take the problem spec, produce an algorithm, express that algorithm in C. Using relatively simple stuff, so variables, assignments, various Boolean operators to do tests, then relatively small number of control structures. C has a few more than that. Standard I/O, library functions. You can define your own functions. You can use return to return values from function, and so on. So I don't assume that you're going to know this stuff, but I don't really care one way or the other about link structures, ADTs, and sorting, but recursion and bit operations are some of the things I'm going to look at in a moment, plus some other stuff. So type def, did you do type def in 1511? Yeah. I should do it on Ztings, then I'd get more answers. Okay, so basically type def just gives a name to an existing type, and it's kind of useless in that context, but it is useful in a context like this. So we can give a name to a struct, and then we can use the struct name later on. Even when you've got things like this, so long int, you don't want to keep typing long int all the time, so you can do big int. You could in fact do the same thing using a hash define, except you do it in the other order. Hash define big int to be long int, and then whenever you put big int in your program, it would be replaced by the preprocessor by long int. So assignments, one thing that we don't tend to do so much in COMP1521 is use the return value from an assignment. So normally we just treat assignments as a statement, variable equals expression. We evaluate the expression when we store the value in the variable. But in fact, that statement is actually an expression, and we can use the value that's and the value of that expression is the value that was stored in the variable. So if we go x, well, here x is assigned 5, that actually returns the value 5 as well. So we could say y is assigned x is assigned 5. So it will evaluate 5, store that value in x, that'll return the value that was stored in x, which is 5, and assign that value to y. So often you'll see things like this, where you're setting up a bunch of variables all at once using assignment statements. So what that's doing, it's treating an assignment statement as an expression. So it evaluates that expression. In fact, let's start earlier. It evaluates that expression, stores the value in z. That's an expression which returns a value 0, and it stores the value 0 in y. That whole thing up to that point is an expression that returns the value 0, and it stores that value in x. So assignments as expressions, generally useful, but of course, as I'm sure you would have seen at some point in your programming career, that can be annoying. If you forget that the equivalence test is double equals and you accidentally write a single equals, depending on what's on the left-hand side of the equals, you're not necessarily going to get the result you're expecting. One thing that this is going to do, it's going to wipe out whatever value is in x to start with. The other thing that's going to happen here is this expression always returns false, so the if part never gets executed regardless of the value of x. If x was 0, we're still not going to do the if part, we're always going to go to the else part. But I'm pretty sure the C compiler will warn you about things like that anyway. One place where using assignments as expressions is really useful is in writing loops like this. So we've got, we call a function that returns a value. We want to assign that value to a variable, and then we want to test the value of the variable. So we can do it like that. The alternative, if we didn't have this idea of an assignment being an expression returning a result, we'd have to write it like that. Which, okay, it's not too difficult in this context, but if there was something more complicated going on, it would start to be slightly annoying. And it's, you know, as a C programmer, it's annoying anyway, because we have to write an extra line of code to do it. And as C programmers, we don't want to write extra lines of code where we don't need to. So those two pieces of code do exactly the same thing. And they do it because we call getChar. getChar gives us a value, we assign it to CH. The value of that assignment is the value that was stored in CH, and then we check whether that value is equal or not equal to EOF. Right, now you may notice that in the colours didn't quite come out that well. Of course, you'll notice that we have parentheses around this. So I've got parentheses around the assignment statement. What would happen if we didn't put those parentheses? If we just wrote it like this, which looks a little bit similar. Any suggestions? I think I've got this in a file somewhere, so I'll jump. I thought I had it in a file. Interesting. Let me put it in a file. So this is what we've got. How C is going to interpret this is as follows. It's going to interpret it like that. Right? So what does that mean? It means we fetch a character from standard input, we compare it to EOF. If it's not equal to EOF, we return a value true from this expression, and we assign that value to CH. So we're not actually assigning a character value to CH, we're assigning a Boolean result from testing whether the next character we read was equal or not equal to EOF. Okay. So think about that. That clearly isn't going to work very well, and in fact, So what's the program going to do? Or, asking the question another way, how many times is that loop going to execute? Or how many times is the body of the loop going to be executing? And I reckon the answer is 0. So we read the first character. Generally the first character is going to be not equal to EOF if we've got a non-empty file, in which case we'll return the value false. We'll assign the value false to CH, so we haven't assigned it a character value. And then the value that we assign to CH is the result of the test expression. So the very first time we call getChar not equal to EOF, false, assigned to CH, false, therefore the loop terminates straight away. Now, even if the file was empty and the first time we, no, oh, what's going to happen if the file is empty? Right, so the first time we do getChar, it returns the value EOF. So getChar is not equal to, so, actually I think I got it wrong before. Right, if the file's empty, getChar, yeah, I got it wrong. Right, so if the file's not empty, getChar will not be equal to EOF, that'll be true, we'll assign the value true to CH, and we'll go around the loop again. And we'll just keep doing that until eventually we get a value false from that test expression. If the file is empty, the very first time we call getChar, it will return the value EOF, not equal to EOF is going to be false, and then we terminate the loop straight away. So if the file's not empty, it's going to actually read through the whole file until it reaches the end of file, but doing something with CH is never going to do what we think it's going to do, because the value of CH is always going to be the result of that test, which is going to be false, which is going to be true, which will be some random non-zero value. Okay, so it won't be the character that we read, it'll be the result of that test. Alright. So generally we ignore the value that's returned by an assignment, except in the context like the one I just showed you, where we're doing while CH equals getChar not equal to EOF. Sort of converse to that, there's a lot of functions that we'll call in C that actually return a value, but we generally ignore that value. Think scanf, think printf. So these two common functions. Printf actually returns a value, which is the number of characters that it printed out. So if we look at this example here, what value is printf going to return? And once again, I've set up a Zeetings, and I'll let you have a go. So if you go to that, there should be a thing like this. So you have a number of choices. Maybe it returns 0, maybe it returns 5, maybe it returns 6, maybe it returns 7, maybe it returns -1. So what do you reckon? Given that it returns the number of characters printed. There's actually two correct answers, one of which would be a lot more common than the other one. Oh, come on, have a go. You're scared. Right, now I have to go back here so you can see what the Z-Tings thing is. It should, if you're already on Z-Tings, there's probably an arrow that you can just go on from the original one asking about what course you did to this one.
Oh, wait, what?
What is a bunch of chickens? No one wants to have a go. Huh? Does that URL work?
What is asking? Yeah. Oh, I thought it was asking what the free document.
Oh, what have you found?
Oh wait, where?
Does it go to the wrong place? Oh. Oh, all right. I give up. If I stuffed up the URL and you can't see it, that's probably why no one's filled it out. Yeah, no one's filled it out. Right, there's the proof return. All right. Anyone want to yell out a guess?
D.
D. What was D? Right, yell out a number. 7. Correct. All right. Why is it 7? Because X is 123, so it's going to print out those 3 digits, then it's going to print out a space, then it's going to print out the 2 digits of 42, 6 characters so far, and then it's also going to print out the new line character. So that'll make up the 7 characters that get printed out. Remember, \n is a code that represents a single character value. So %d is replaced by 1, 2, 3, then a space, then 4, 2, and then new line character. Interesting. I wonder why that's wrong. Alright, so ignoring return values in some contexts is okay. Normally we don't care. Oh, the other thing I should have said, if printf screws up and for some reason it can't print anything out, I think if you go down to the bottom of the definition for a library function, and printf would have to have the longest definition of anything. Compatibility, errors, standards, also where's the return value? Wow. Damn, I think I might have gone past it. But I suspect if for some reason printf can't print a value, it might also return the value -1. So in theory, potentially it returns 7 if everything worked alright, and -1 if it didn't. And that's a general property that we're going to see a lot when we look at system calls. System calls are basically a request to do something, but what you're trying to do might not be allowed, or it might fail for some reason, and what the operating system will typically return in that case is -1. Otherwise it'll return some value that's relevant. So if you say read in 100 characters, and it can read in 100 characters, it may return the value 100. If you try to read from something that's not an open file descriptor, then the attempt to read will fail, and the operating system will return -1 to tell you that something's gone wrong. And generally what happens is that, in fact always what happens, if there's an error, we'll set the value of this global variable, which is available in every C program you write. And if you want to print out an error message based on the value that it stores in here, so there's a whole range of possible error values. You can go and look them up in the manual. If you want to find out what the error was, there's also a function called p-error that will print out a message based on the error value that was stored in the errno variable. So just remember that, because we're going to see that a lot once we start talking about system calls. We put in a request to the operating system, ask it to do something. If it can't do it, it'll typically return the value -1, set the value of error, and if we actually want to find out what the error was, we can use p error to print a message corresponding to that error number. Right, another aspect of C that may or may not have been covered so much in 1511 is control, fine-grained control over the execution of the program. I'd call coarse-grained control a while loop. So you just run your while loop and your while loop and your while loop keeps running until the continuation condition becomes false. So until you work out that you can't do any more. So for example, while CH equals get char not equal EOF. So if CH eventually is equal to EOF, the loop will terminate. And if we're inside a loop and we only want to execute part of the loop because we're interested in some condition, so maybe we only want to do something if the value that we read in is greater than 0. Then we put in an if statement and we have part of the loop to do that. Another common example of a good programming style is that you do all of your computation in a function and you have a single return at the end of the function. And similarly, the only way that you ever exit from the main program is via the return at the end of main. So C provides ways of not following good programming style, but which I would argue often make the code easier to understand, despite the fact that some people regard them as bad style. So for example, you can use break and continue. Break will allow you to exit the loop, the enclosing loop. Continue skips the rest of the body of that loop. I'll have a look at an example in a minute. It's often extremely useful to do a return from a function at some point in the middle of the function, as well as having the return of the normal result at the end. Very common example for doing that is if you're writing a function, you're trying to do something, maybe the function is not going to be able to do it, maybe you ask for the factorial of a negative number or something like that. You can check right at the start of the function whether the parameter to the function is valid, and if it's not, then straight away you could return some error value like -1 if that's what you want to do. So having multiple return statements in a function. So we're going to use all of these constructs as we write code throughout the semester. If you want to terminate a program early, one common way that you could do it is a function returns a value, an error value, and then that error gets propagated through the main program using more if statements, and eventually we return from our main program. It's much easier that if you recognise an error condition at a certain point and you don't want to keep computing, you can just exit the program at that point. Similarly, you probably used assert in 1511, so that basically does a test. If the test fails, then the program exits straight away and it prints a message. So here's an example, once again, two pieces of code that do exactly the same thing. One using break and continue, and the other one using good style. Okay, so here we've got a for loop. The continuation condition is that I hasn't reached the value of n, and we haven't encountered a 0 value in the array. So this is scanning an array. I would argue that a simpler way of writing this is to have a very straightforward for loop, just for I equals 1 to n, 0 to n minus 1. And if we happen to encounter a 0 inside the array, we simply break the for loop. So we jump out of the for loop and we're done. Obviously this is going to do exactly the same thing, but my argument is that this is a very simple expression. You can see quite clearly what the loop is intending to do. It's just iterating over the array. The fact that it may stop early because it finds a 0 value in the array, we can handle that there. And similarly, if we end up with a negative value in the array, we don't want to include that in our sum. So if we discover an array value less than 0, continue will take us to the next element in the array. So the continue here will do the I++, then reevaluate that condition and then come back into the loop. You achieve exactly the same effect down here. Now, like I said, this is a bit of a contrived example, but you can easily come up with other examples where doing things this way makes the program a lot simpler and easier to understand than doing something like this. Right, so all of those C constructs are going to get used throughout the semester, so make sure that you're familiar with them. A couple of important data, I haven't quite finished yet. Maybe I will actually finish soon. A couple of really important data structures that often get used inside computer systems. Stacks, we're going to see that a lot I've already used the word stack when I was talking about the memory layout. So the way we build up chunks of information related to functions is in a stack-like model. Queues, when we're talking about running lots of processes together and trying to organise when a particular process runs, we often put them in a queue to make sure that the first process that came along is the first one that gets run. On the other hand, we might be interested in saying, I want to make sure this particular process runs first because it's more important. So in that case, we'd use the priority queue. And I gave you too much of a queue that we were about to stop, so let's stop there.